Something truly amazing about calculus is that the derivative of e to the x is e to the x again. E to the x is the only function that has this property, and it really shows how fundamental, I guess how natural, e to the x is to calculus and really mathematics in general. It's really kind of, along with natural log, e to the x and natural log of x are kind of the cornerstones or anchors of a lot of calculus. Can be brought back to what happens with e to the x. So let's prove that the derivative of e to the x is itself e to the x. First, we need a definition of e. And you'll get a few of these definitions of e as you go along with calculus. There's several, but today we'll do one as follows. So imagine an exponential function y equals b to the x. Actually, imagine several of these for a bunch of different bases, b, right? It can be 10 to the x, 2 to the x, all these different things. Each one of these exponential functions will have a different slope of the tangent line at the point x equals 0. So the point that of interest here is 0, 1. Right, so 10 to the x is going to have a steeper tangent line, 2 to the x will have a more gradual tangent line, not as steep. But only one of these exponential functions will have a tangent line with slope exactly equal to 1. So whatever that number is, we don't know what it is, we don't need to know what it is, but let's call it something. Let's call that number e. So equals e to the x. Anytime it has a slope of 1, there's only one such number for the base that can give us a slope of 1 for the tangent line at the point 0, 1. Let's call that number e. And in fact, that will be our definition of e in this context. So here we go. Here's our definition. Let e be the unique number with the property that f of x equals e to the x has a slope 1 at x equals 0. Only one such number will have that property. Let's call it e. Right? Because how else could we talk about e, right? We could say, 2.7, or maybe 2.7, or then do we say 2.71828, 1828, 459045, blah, 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 right? We would have to talk about it forever to actually say what it is. So we can't say what it is other than by using these non-direct ways of talking about it to define it without actually listing out all the digits, because we never can. So we can get even more detail out of this, which will be useful for the proof. This tells us that this function, f of x equals e to the x, if we take the derivative at 0, the slope of the tangent line at 0 must be 1. But we have a limit definition for that. Let's actually go down here with it. So this is the limit, if you recall, as h goes to 0, of f of x plus a, or f of a plus h. We'll use the definition of the derivative at a point. So f of a plus h, so f of 0 plus h minus f of a, e to the 0, all over h, all over h. Okay, so we know that this must be equal to 1. But we can simplify this a little bit. This tells us that the limit as h goes to 0 of e to the h minus 1 all over h equals 1. Okay, so let's stick a pin in that. We'll come back to it later and use that as part of the proof. Okay, so now let's prove the whole thing. So here's our claim. I claim that the derivative of e to the x is e to the x. Okay, proof. Okay, and we're still using our same function here. So here's our proof. F of x equals e to the x. F prime of x then is the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's e to the x plus h minus e to the x all over h. Okay, well we can factor an e to the x out of that top bit there. So limit as h goes to 0 of e to the x. What does that leave behind? E to the h minus 1 all over h. Well, this e to the x has no h in it at all, so that's going to pop out to the front of the limit, since as far as the limit is concerned, this thing is a constant, because the limit's looking at h's, not x's. So that comes out to the front, leaving us with the limit as h goes to 0. Let's bring that e to the x out to the front. And then we simply have e to the h minus 1 all over h. But remember that that exact quantity, that limit as h goes to 0 of e to the h minus 1 all over h. That's already equal to 1. We already know that's equal to 1. So this gives us e to the x times 1, which is e to the x. And that's what we sought out to prove. All right, so we get to do our little proof box there. And there you have it. Let's do an example of taking the derivative of functions involving e to the x. Or in this case, e to the w. Okay, so here we have the function in an example. G of w equals the quantity e to the 2w plus e to the w all over e to the w. And we're asked to find g prime of w, which is the derivative, of course. Well, we still don't have a quotient rule. And honestly, we wouldn't want one here because we can simplify. And you should always simplify before you go about using some crazy rule. So look, we can cancel an e to the w. How about this? Let's rewrite this g of w as, let's factor out e to the w. How about that? Out of the top there, that leaves us with e to the w plus 1 left behind. And then we still have e to the w in the denominator. And look at that. They cancel right out. So now we have g of w equals e to the w plus 1. And we can very quickly go then to g prime of w. Well, it's simply e to the w again, because remember that the derivative of e to the anything is e to that thing again. And then the derivative of 1 is 0 since 1 is a constant. So there we have it. E to the something is pretty much the easiest derivative we'll have in the entire course because you just write it again. Now it'll become a little more challenging when there's a function up here. We'll have to do something called the chain rule, but even that is not so bad when you're dealing with e as your base.